In this video, I'm going to finish up this example of the coupled springs, the coupled oscillators. And to where we left off in the previous video was that the initial condition for the position of the first system, the system that is moving, the two masses are moving simultaneously in one direction. We can find that by taking the projection of the basis 1 onto the state that describes the initial position x0. So if I write that out, then what I have is the basis vector 1, 1 multiplied by the other state, which is x1 x2, like so. And now if I was to multiply this out, I would get 1 over the square root of 2 times the initial condition for mass 1 plus the initial position of mass 2, right there. Now if I work this out for the second system, the system where now both of these masses are moving in opposite directions with each other, like so, then it's the same thing. It's projection of basis state 2 onto the initial condition, which I can write out now as 1 over the square root of 2, 1 minus 1 times the initial position of mass 1 times the initial position of mass number 2. And when I now multiply that out, I get 1 over the square root of 2, x1 initial minus x2 initial, like that. Okay. So now, if we were to put this all together, so what we would have is a position vector at any moment in time t, which is our basis 1 times the initial x1 initial plus x2 initial over the square root of 2 times the cosine of omega 1 times t plus the possibility that the two masses are now moving as in state 2, where they're moving in opposite directions of each other, times the initial condition x1 minus x2 divided by the square root of 2 times the cosine of omega 2 times t. Okay. Now, what is the position of mass number 1 at any moment in time? Well, now that's just taking the projection, now not in our diagonalized basis, the basis where we're using Roman numerals, but this is now the basis of just mass 1 moving by itself on our position vector x of t. And so if I was to write that out, I would have 1 inner product with the basis state Roman numeral 1 times the initial condition times the cosine of omega 1 plus the basis 1 times the basis Roman numeral 2 times the initial condition for state number 2 times the cosine of omega 2 times t. So basically, what am I trying to do here? What I'm trying to do is make a change of basis. So I've solved the problem in terms of the basis where this diagonalized basis, where the object is either the two objects are either moving simultaneously left or right, or their breathing mode where they're moving in opposite directions with each other. And now I'm trying to project it back onto the original basis, the first attempt that we did, where only, say, basis state 1, the Arabic one, is now the basis for only object number 1 moving. So I'm trying to combine basically the two results. We solved the easier problem of the decoupled differential equations in this basis, diagonalized basis state, and I'm applying it now to just the previous one, the coupled equations basis state. Okay, so if I look at this, the inner product of Arabic 1 with Roman numeral 1 is 1, 0 times 1 over the square root of 2, 1, 1, which basically gives me 1 over the square root of 2. The inner product of 1 with basis state 2 is 1, 0, 1 over the square root of 2, 1 minus 1, which also gives me a 1 over the square root of 2. So now we're trying to put all those pieces back together. We can do this now for trying to project state number 2, basically mass 2 moving by itself, onto our solution of basis state 1, initial conditions, plus 2, 2 inner product with diagonalized basis 2, initial conditions, times the cosine omega 2 times t. Okay, which means now if I work out these inner products, I have 0, 1 times 1 over the square root of 2, 1, 1. So that gives me 1 over the square root of 2 as this factor, and then 2 projected onto diagonal basis 2, so that's 0, 1, 1 over the square root of 2, 1 minus 1, so that gives a factor of minus 1 over the square root of 2. And so now, if we put it all together, we've got all these pieces we get to put together, the position of mass number 1 would be 1 over the square root of 2 times the initial conditions times the cosine of omega 1 times t plus 1 over the square root of 2 initial conditions so now if you just multiply those factors together, you get basically the sum of the initial positions of both masses divided by 2, basically their average position, times the cosine of omega 1 times t plus the difference in their positions divided by 2 times the cosine omega 2 times t. Basically we can get a similar result for position number 2. For mass number 2, what's its position as a function of time? You would get x1 plus x2 divided by 2 times the cosine omega 1 times t plus, minus, because you got to remember there's a factor of minus 1 over the square root of 2, minus the initial conditions divided by 2 times the cosine of omega 2 times t. Where, if you remember, omega 1 was the square root of k over m, and omega 2 is the square root of 3k over m. So basically now we've solved the problem. We have functions, x1 as a function of time and x2 as a function of time, and we've worked out all of the normalization factors. That's what gives us the divide by 2 in these equations right here. We have the sinusoidal behavior of the cosine. We've got the eigenvalues, which are basically the angular frequencies of the oscillation of either mode, either the coupled mode of the two moving in the same direction, or the breathing mode where the two masses are moving in the opposite directions of each other. All that's put together, and now the only input that we have to put into this problem is what are the initial positions of each of the masses at a time t equals 0. So when we put those two numbers in, and then we let the system run, we can now predict where each of those masses are going to be at any given moment in time. So it took 3 videos, but we eventually worked through this problem, and we did it in a way to show that if we used these operators and we pick a basis that diagonalizes the operators, then our life is made so much easier. And not only that, but it also gave us some physical insight, because now we know that the system can move not just two masses moving around in different directions, but we have the two masses now moving in unison, or the two masses now breathing, moving in opposite directions.